So for multiple MI300A CPUs, so for the CPU side, we could do threading like we usually do on the CPU. And you don't need memory movement because you're on the CPU. So when we move to the GPU, we have to worry about the memory movement. So let's look at real-world OpenMP language constructs. So let's break down that compute directive. We don't often actually break it down in our program, but understanding what each one of these do is really helpful. So the target is going to launch that code to the GPU or data, if we can actually use that on a data element, a data array as well. Teams is a league of teams, and it isn't very clear what that means in the OpenMP standard. So I'm going to show you that. But each team would then operate with a single thread. Distribute means the loop iterations will be distributed. Parallel, it's going to create multiple threads. And then for do, it's going to spread out the work across those threads. So parallel just creates those multiple threads. The do is what spreads it out across the threads that are created. So it's like if I do one, I want to do another one of these clauses. And then SIMD, we said, doesn't really do anything on this with this compiler. So loop will replace all of those in OpenMP 6.0. So here we're seeing that OMP target directive, which is just going to offload to a single thread on the GPU. And then we see the teams. We can add target teams. We can add target teams distribute. So there is an order that is required in these clauses. And then the loop will replace the distribute parallel 4, but then Open 6.0, they added the loop directive would work even if you don't have teams. So those are the compute directives. But let's see what that looks like when we move actually onto a GPU, which is, see, the OpenMP standard doesn't want to talk about the GPU because it's for any device. It could be for an FPGA. It could be, a device that isn't even created yet. So let's look at what happens when we put Pragma OMP target. It's going to launch one work group with one thread. So that's actually going to be a lot slower. It's basically going to be a serial code on the GPU. And if we do that on an APU, it doesn't need to move the data, but it's still only using one thread and one work group. So that's generally not what you want to do. But there's sometimes, I only got one thing to do, target is enough. So let's look at the other subsets. So we have OMP target. We can also do OMP target teams. Well, that will create multiple work groups. Okay, so teams and work groups are the same thing, even though the OpenMP standard never tells you that. They're the same thing, at least with almost every compiler. So it's going to launch multiple work groups, but it's still one thread on each work group. Also, the crazy thing is that every work group is going to go from 0 to N. So we may be creating a race condition. Who knows what's going to happen here? Generally, this isn't what you really want to be doing, right? But there may be cases where that's all I need to do. Distribute now, in the distribute in the lower left, now you see that loop is broken up. And the first work group is doing 0 to 3, the second work group 4 to 7. And on through the work groups until we get to all the work being done. But I'm still only using one thread. Okay, so now I got to add parallel 4 to launch more threads. So parallel is going to launch the threads. 4 is going to say actually use them. Okay, so there is a point to every one of those clauses, even though we don't generally use only a few of them. But if I only had 100 things to do, maybe I don't want to use all the work groups. Okay, maybe I want to do less. So I could actually, there may be some cases where it makes sense, but it's very, very seldom. So the OpenMP standard really likes to keep this idea of a generic device. And so compiler implementations may vary. And some of these combinations may not make sense, like distribute without teams. If I haven't created teams, how do I distribute? And the AMD compiler will generate an error for that. But that's not necessarily guaranteed. The standard does not say what to do there. It just doesn't make sense. It probably should say something about that. At least you have to produce an error. So here we have a very simple Saxby program, single precision AX times P equals Y. So we're going to put that full directive on it, but let's see what happens when we do subsets on here and what happens in reality. So we can add, and I'm starting to give you information about how to tell what the compiler is doing. So if I do add export libomp target kernel trace equals 1, it's going to give me information about what the compiler does. So if you were trying to figure out why, and there was a question earlier, what is happening? Why isn't this behaving the way I think it should? Adding these environment variables will tell the compiler to give you more information back. This is absolutely critical because it's hard to tell what the compiler is doing. If I don't get that information back from the compiler, I probably am thinking that it's doing something different than it actually is. So with this environment variable, and I give it that compute directive, it's going to dump out this information you see here in the box. It's going to tell me what workgroup size it's using. It's going to tell me how many threads. So it's going to launch 416 workgroups, each with 256 threads. So that's my workgroup size, 256. It's going to tell me how many vector registers, VGPR is vector general purpose registers, SGPR is scalar general purpose registers, and it's going to tell me how long it took. And the more recent compilers will even give you occupancy for that loop. So let's see what that looks like when we do the subsets of that parallel compute directive. So if we just do OMP target, it's going to do one work group with 256 threads, but only one thread is doing anything. And we see that the runtime is 5.4. And if we do target teams, it's going to launch a whole bunch of work groups, but still each one of them is going to do all the work. So it actually is slower. Because I just got more of them. They're all doing the same thing. They're all doing the whole loop. So it actually is going to take longer. If I do target teams distribute, now I'm starting to make some headway. And I got 624 work groups, each with 256 threads, and the kernel starts speeding up. And then if I do target parallel 4 without teams, okay, so here we're leaving something out. So we don't have target teams distribute parallel 4. We've left teams and distribute out. So we only have one work group, 256 threads, and you can see it's 0.12 for the time. And for comparison, the original with the full compute pragma was 0.08. And so there may be cases I know I don't have that much work. I'm not going to allocate as many work groups for that loop. So there may be cases where you do this, but it's rare. Okay, so everybody's starting to understand what all those clauses do to your compute pragma. And this, it's not many places you actually see this explained, because we don't usually break it apart. Looks like went the wrong way. We can also break up that compute into two lines. So we could have our outer loop with part of that compute directive and the inner loop, the other part. This is occasionally done if you really know what's going on with the loop, but I would strongly recommend just use the collapse clause instead. Maybe some rare cases where this makes sense. So I may know that I don't have that much work in the outer loop. I'm going to break that across the work groups, and then the inner loop I'm going to parallelize across the threads. So here's an example of that where we break those two up. The inner loop has the parallel 4, and the outer loop has the teams distribute. Okay, and this will work. I still would recommend here most times that we would use the collapse instead. If you've got like 6-dimensional problem, this may make more sense to do this, to have the outer loop. You don't want it to parallelize the outer loop, and you want it to do the inner loops. So when you got many nested loops, it might make more sense to do that. Sometimes we actually don't want to parallelize the outer loop at all. We want to do the inner loops. And a lot of the codes I've worked with, you, especially object-oriented, you get the inner loop is like 1 to 3 for dimensions or some other small loop. And you actually want to unroll that loop because you want the inner loop to be a large dimension. So causing that inner loop to unroll can be a good strategy when you have a very small inner loop. Okay, and this just shows what happens with that split level directive, and it only shows the what the compiler generates, I think, for the outer loop. So it doesn't show both loops. You only get the report for the outer loop for some reason. And the occupancy is lower and our runtime is slower. So usually let the compiler do the optimization and don't over optimize with your directives. Don't try to be smarter than the compiler on these things. There are some other clauses that we can use. Tile is actually something you might try, especially with stencil codes. We can create a tile, and it's sort of like blocking the loops, if you've ever done that technique for optimization to make your memory more local. We can force the number of teams or the number of threads. This is sometimes effective when you know more than what the compiler can see, and you know that it doesn't need to allocate a bunch of work groups because there just isn't enough work to do. The ones that are most common, though, are the num threads and thread limit. And that's because we can reduce the work group size. That gives us more vector registers to work with, or more shared memory on the GPU for the threads to work with. And you'll hear this terminology that I've got memory pressure or vector register pressure. GPUs were really designed to put triangles on the screen. They don't have a lot of memory. And if you give it a 500-line physics loop, it's going to run out of registers to work with, even though there's more registers on a GPU than on a CPU. It's just going to run out of registers and it's going to slow your program down. So the trick is to reduce your work group size so you have more memory resources to work with. So num threads and thread limit can be a way to get a little bit better performance out of your kernel by forcing it to use work groups. A reduction, that's another very common case. We want to sum an array into a scalar or a multi-dimensional array into less dimensions, maybe a vector. And you can add no weight. There's an implicit weight at the end of each loop. So this thread limit is going to tell the compiler what the maximum work group size is, and that allows the compiler to generate more efficient code. And you can use both thread limit and num threads together. So thread limit means I'll never call it with this many threads. Num threads means for this case, I'm going to call it with a specified number of threads. Well, how do I know what threads and what teams to use? Well, you can use Rockham Info to get the information out about your system. How many, so you can get compute unit is 110. SIMDs per compute unit is 4. And so that can give me some hints what to put into these clauses. Again, though, I generally would let the compiler deal with this. It usually does a smart thing. For the most common clause you're going to use is a reduction clause to say I'm summing. And I'm going to point out some things here that people often get wrong with OpenMP. So OpenMP says that it will initialize the reduction variable in the loop. So in this case, it's a sum, so it's going to initialize sum to 0. If you're doing a max or a min, it will do the appropriate setting for that variable. Now you see I've got double sum equals 0 here. I don't actually need it when I'm compiling for OpenMP. But this would fail in serial. With good practice, put it in. You see, here we're going to do the data map here. So you don't need that if we're on an MI300A, but this is the syntax we would have on a discrete GPU. Notice what's in red here. I see this very, very often. So you see private of I. Loop variables are private by default. Specifying private generally is not going to hurt, but it's not clear what that behavior is by the OpenMP standard. So I would leave that off. Map to from, we do not need to map the reduction variable. Okay. If we map it and the compiler is doing it already, what's going to happen? Undefined. NVIDIA actually at some point, I think it was PGI, you actually had to map the variables. So we see some code like that. And then you see the reduction that is required. And the standard also says the result will be copied back to the host by the standards. You don't need to do that. Okay. Initialized and copied back. So while some of these things will generally work, I don't recommend it because it's undefined behavior. Now, real world cases and a lot of the codes I worked with also did a reduction into a vector. So let's say climate, I wanted to sum all the contributions of the ocean up to in a column, or in the atmosphere, I wanted to sum what was happening in a column of air. Or you're summing up reaction energies into a particle array. So reducing into an array variable from a 3 or 4D array into a one-dimensional array is very, very common, and most of the compilers did not support that. It was a bear programming around that. Right now, with the AMD compiler for C and C++, that works fine. Fortran, I think they have fixed it now, but that was missing in the Fortran compiler until recently. If you're using the Cray compiler or some of the other compilers, that may or may not work. So you test that. But that was one of the things that was really, really crucial for the compiler to support. So here's an example of a reduction to array. And one of the purposes of our tests and our examples is we actually run that on the system after loading up the compiler and the environment to see what fails. And some of the things we have in there are things we asked for, like this reduction to array, to find out when they get the support working. So here's the syntax, and you won't see this many places. What is the actual syntax for the reduction clause if it's an array instead of a scalar? So you see the sum, square braces or square brackets, 0:n. I'm going to copy that whole array as the reduction variable. The other thing that causes a lot of difficulty in real codes is calling a subroutine from a target region. So I have this target region. This region, the whole region is being done on the GPU, but I call a subroutine. In the original OpenMP, you had to inline everything into that code. But now you can call it, but you have to tell the compiler you're going to do this. And not all the compilers support this equally well. There's some variation in how they're supporting it. So the way you do this is with this OMP declare target before and after the block that is your subroutine. And C, it can figure out what the block is, so you do not need this. And I think in Fortran, you actually don't need the end as either, but it is optional. And the same thing with the data. So I may have data that's in that routine that I'm declaring target. And the compiler has to know that it has to be over on the GPU as well. And so you have to do this OMP declare target around the data as well. That causes a lot of complexity and confusion among programmers, especially since you have to do all three of these at the same time. People start wondering, well, I put that on there, but it's still failing. And then the compilers vary a little bit in how they implement this. So understanding how your compiler does this is really important. So there's an example of this in the exercises. And so we're going to declare the data target. We're going to declare the compute routine target. Now there's a note for the LLVM compiler. If this is all in the same file, you don't need all of that. I still recommend putting it in there because you're going to get surprised when you split things and all of a sudden it quits working. But here the compiler this is what they call implicit declare target. It can see where it's being used and it will do it for you. So if you're doing, this is the problem. You do a simple program, it looks easy. And then you try to do your complex program and you get surprised. Okay. So this is probably the area we got the most questions about. And people would send us bug reports, which was many of them that were invalid code, saying this doesn't work, but it's partly they didn't know how to do it. And then they tried a whole bunch of different things. Nothing seemed to work. And they sent us their last attempt, which was a mangled mess, as you can imagine. So that's one of the reasons why we include this. It is complicated. We also have an example, what happens if it's a dynamic array? You can't just do declare target. That's only going to copy the pointer over. So now I got to use the enter data as well. Okay. So real world cases get complicated because of these complex combinations of these different language constructs. Where we really get into trouble is if you're doing stuff with structs or classes. So we got a bunch of examples in the exercises for these cases that you can look at. What happens if I got a structs? Because it's going to copy over the structure, but if you got a pointer in the structure that's been allocated to an array, it's not going to copy that. That's called a deep copy. So you have to do extra effort to move those deep copies over. In any of these programming languages, by default, they generally don't copy. They don't look at it and say, I've got to, this is a pointer, I got to copy this data over. The latest OpenMP standard has a way to do that mapping of that deep data, deep copy data. It's a little tricky to do though. So here we have dynamic arrays. In this case, we're going to allocate the data, and then we're going to, because this array may be a different size, depending on the input, we're going to allocate it later. If we just do this OMP target data, it's only copying the pointer over. So here it's showing that enter data alloc of that array, and it's preferable to set it in that loop on the device, but you can also set it on the host and copy it over. It's just hard to catch all these cases. And I know in some of the codes I worked with, you're trying to do, you got thousands of subroutines, you're trying to catch all these issues. Again, you know, you can imagine how the MI300A is going to make some of this easy. Don't have to worry about the data part. So this is showing a dynamic array as part of a structure. And here we're going to have to use that enter data to move that array over. So you're moving the structure over, but you've got to move that pointer over separately. There's also some subtleties about whether you want to do a release or a delete. And some of this is compiler bugs, but release is doing a reference count. And so it will only delete when the reference count gets to 0. Delete will force the delete. And there are special cases where usually you could use either one. There are cases where they are different. So, you know, the OpenMP standard is adapting for more complex code, and each release of the OpenMP standard and the compilers is allowing you to do some things that are much more complicated than the original OpenMP. You gain some portability, but you also need to test on each platform some of these language constructs we're talking about and see if they're handling it slightly differently. I know we had a case that we're doing a workshop in Stuttgart this week, and the Cray compiler is a little different than the AMD compiler, and so it's in clauses I'm not even showing here, but there's differences you need to check before, so that you can write code that is portable. And if you go into if you bring down the examples repository, there are some really good readmes in there. You can walk through them and experiment with it and see how it behaves. And not only, you know, what I'm telling you here, but check with your compiler and your compiler version to verify what is supported and what is. Okay. And we're really prioritizing those language constructs there's no way to work around, especially in the Fortran compilers. So if you have something that is just not working and you really need it, please let us know. Okay. So for this section, there's C, Fortran, and C++ exercises to go along with this. For example, in C++, it looks at what happens when you have a class, and experimenting with this sort of target function. How do you do that in a class, and what is supported? So you might look at that. In Fortran, there are cases with submodules you may want to look at if you're using submodules. So I strongly recommend walking through those examples and just trying them out and looking at them. And there's a whole bunch of them. We actually have a course coming out where we go through these in much more detail. And University of College London is putting it together and with Jupyter notebooks and Moodle. So you goes into much more detail stepwise into each of these language constructs. And they are willing to license out that course if there's anybody interested in translating it to Japanese. It might be kind of nice because it's online what we've just gone through, but even in more detail. So we might try to do that at some point. Questions on those language constructs? Real code gets messy.
Do you want to reduce twice, like 2D first and 1D? How would you do that? Like you always reduce in one
Yeah,
direction.
you could reduce into an array and then reduce that array into a scalar.
Directly and just two line, two
Separate.
pragmas. Okay. A separate loop and then a pragma individually.
That would be a nice example. Can we do that all at once?
Yeah.
Yeah. See, this is the problem. We get people who do crazy things with code. No, I mean that really. I mean,
Yeah. It's happened all the time.
you see the compiler guys, you know, they think that the longest a program can be is 12 lines. And then we throw real physics code at them and they wonder why, you know, we have all these issues. It's because you get, I mean, it's amazing the complexity we get in our real codes. The other, what I did not mention here, you guys got to ask me more questions. You didn't ask me about array syntax. Array syntax is so beautiful in code, and you end up having to basically unroll all those array syntax into real loops. Which make, especially when you're doing some really fancy stuff in Fortran, it can make the code a lot uglier and longer. But the compilers really don't know how to handle array syntax right now.
Or if you use all these libraries in C++, like whose libraries, I don't know how.
So if you're trying to get to the GPU, the lesson really is to stay simple. Because you get too complicated. And some of the Fortran codes, we ended up, you know, unrolling all the array syntax, and it's how ugly do I want to make it to get performance I'm willing to accept. And if I really want all the performance, the code is just too ugly. So there's a balancing point there, how, you know, how much I'm willing to have simpler, more elegant code versus fast code. And that's just the reality with Fortran, because you can do some really crazy things with array syntax. And basically all compiler writers still are working in the Fortran 77 era. They think of it as arrays. They don't really think array syntax for optimization. And there are some real issues. If I've got a line, an array syntax in a line, that basically is a loop for that one line. And if I've got a bunch of those, it's going to be doing a separate loop for each one. Will not be the most efficient way of doing something. So you have to know when you can fuse that data, when you got to split the loops to be most efficient. And that's a real challenge. Both directions, but array syntax makes it hard. The compiler doesn't necessarily know that these two loops can be fused. It doesn't know the sizes. Yeah, so if the same function is called by both CPU and GPU, how can we write it with the OpenMP directive? that directive that I showed you will compile for both CPU and there is another clause you can add to it that says only do it on the GPU. Okay. There's several other clauses, some of which are not well documented and exactly what they mean. This is the problem with the OpenMP standard is you need about 5 people to read it to tell you what each clause does. So the first thing we have to do often with bug reports is have 3 or 4 people look at it and say, what does the OpenMP standard actually say? And they often have a lot of arguments. And that's before you can fix the problem. There was a group out of University of Delaware that was writing tests for all the OpenMP offload compilers. And writing valid tests, they found very, very difficult because it's difficult to interpret what the standard actually says. So they spend a lot of their time just trying to figure out what the correct syntax is. It's not obvious. This is actually one of the areas that AI can be very helpful. AI is very good at reading the standard and saying how to implement it. Instead of you digging through 400 pages and trying to figure out what the clauses actually do. So we have something called the AMD AI Programming Assistant, which we are demonstrating that takes these things in our lecture notes and the documentation from the AMD site, and you can query it and ask it, can you write this Fortran program using target device correctly? So that can be very effective. And hopefully it won't grab something some really bad example. We got to start taking these bad examples out of our exercises so that it doesn't grab them. And there's not a lot of examples. I hate to say it, there is a document on the OpenMP standards site of examples, but it has very low coverage, especially some of these more complex programming cases. So examples are really, really important to have because there's just so few of them out there of real code and what it does. For example, the case you were talking about. Do we have an example of that? Okay, do we have more questions? Yeah, so how well or bad can the AI system insert the directives automatically? If you keep the problem size small of what it needs to do, it's actually not bad, but it's so I like to describe the AI programming assistant as an overeager graduate student. They will give you an answer even if they don't know. And you have to have the judgment, does that make sense? You can have it actually test itself, say, compile this and run it and give me a working example. But you keep asking your questions. It may take 7 or 8 tries before it gives you the correct answer. But it's like this overeager graduate student. It will never say it doesn't know. It's going to try to answer you no matter what. And occasionally it stumbles on a brilliant solution. Okay, so that's why we call it an assistant. Okay, this idea of vibe coding. Not for this kind of stuff. It just helps give you ideas and things to try. So, but it can be really helpful, especially when there's something deep in the documentation that would take you days to find, and it may be able to pull that out. And I don't know if we talk about that in our lectures here, but we have a MI300X node with the AI programming assistant on it that Giacomo has running right now with all of our presentations and exercises. And, you might be willing to put people on that as well. It does take a GPU to do this. If you run it on the CPU, it will, the AI will run the large language model. It will run there, but it's slow. And so to be usable, you really need a GPU. And also for what we use for HPC programmers like you are and I am, we use something called RAG, which is where we supplement the training it has. It may have, the large language model may have been trained in 2023. So it may not have access to the latest stuff. So that's why we put all our training materials, the documentation we have that is recent into them on top of the model, and it will look there first and then use the LLM to analyze it. So we're using that. It really just reduces the searching through all the documentation to find stuff. Okay, I think we have run through this section and through the exercise time. So go ahead and do the exercises as you have chance to. And I think we're into lunch.